Out there in the vast expanse of the cosmos, far beyond our familiar stars and galaxies, lie some of the most fascinating and enigmatic objects ever observed. Quasars. These celestial powerhouses shine with a brilliance that dwarfs entire galaxies, emitting energy equivalent to trillions of suns from a region smaller than our solar system. But what are quasars, and how do they generate such incredible amounts of energy? At the heart of every quasar lies a supermassive black hole, a cosmic monster with a gravitational pull so strong that nothing, not even light, can escape its grasp. These black holes are millions, even billions of times more massive than our Sun, and they are the engines driving the quasar's extraordinary luminosity. As gas and dust spiral inwards towards the black hole, they form a swirling disk of superheated matter, known as an accretion disk. Within this accretion disk, particles are accelerated to incredible speeds, reaching temperatures of millions of degrees. This intense heat causes the material to emit radiation across the electromagnetic spectrum, from radio waves to X-rays, making quasars visible across vast cosmic distances. The sheer energy output of a quasar is mind-boggling, and it is this incredible luminosity that first drew the attention of astronomers to these distant objects. But the discovery of quasars raised more questions than it answered. How do these supermassive black holes form and grow to such enormous sizes, and how can they accrete matter so rapidly to power their prodigious energy output? These questions have puzzled astronomers for decades and continue to drive research into the nature of these cosmic behemoths. The existence of quasars, particularly those observed in the very early universe, presents a significant challenge to our understanding of black hole growth and galaxy evolution. The most distant quasars are seen as they were just a few 100 million years after the Big Bang, meaning their central black holes had to grow to billions of solar masses in a remarkably short time frame. The standard model of black hole growth, known as Eddington accretion, posits that black holes grow by accreting material from their surroundings. However, there is a theoretical limit to how fast a black hole can accrete matter, known as the Eddington limit. This limit arises from the balance between the inward pull of gravity and the outward pressure of radiation from the accreting material. If a black hole accretes matter too quickly, the outward pressure from radiation would overwhelm gravity, pushing material away and halting further growth. According to Eddington limited accretion, it would take an impractically long time for black holes to reach the enormous masses observed in distant quasars within the available time. This discrepancy between the observed masses of early quasars and the theoretical limits of black hole growth has led to what's known as the quasar growth problem. It suggests that our current understanding of black hole accretion may be incomplete, and alternative growth mechanisms might be at play in the early universe. To explain how quasars grow so massive so fast, astronomers have proposed several alternative theories that go beyond the limitations of standard Eddington accretion. These theories explore exotic scenarios and physical processes that could potentially accelerate black hole growth in the early universe. One intriguing possibility is super-Eddington accretion, where black holes might temporarily exceed the Eddington limit by accreting matter in short, intense bursts. Under certain conditions, such as during galactic mergers or interactions, black holes could be surrounded by dense gas clouds, providing a temporary surplus of fuel. Another mechanism involves black hole mergers, where two or more smaller black holes collide and coalesce to form a larger one. In the dense environments of the early universe, such mergers could have been relatively common, leading to a rapid buildup of supermassive black holes. A third possibility is jet-assisted growth, where powerful jets of relativistic particles launched from the poles of a spinning black hole interact with surrounding gas and channel it back towards the accretion disk, boosting the accretion rate. These jets could potentially overcome the Eddington limit by pushing material inwards from a distance. Astronomers are actively researching these alternative growth mechanisms, using sophisticated telescopes and computer simulations to study quasars in unprecedented detail. Recent observations have provided tantalizing clues about the lives of these enigmatic objects and the processes that drive their growth. One such discovery involves the surprisingly short lifetimes of quasars. Observations of quasar proximity zones, regions of ionized gas surrounding quasars, suggest that these objects may only shine brightly for a few million years or even less before fading away. This short lifespan further complicates the growth problem, as it implies that black holes must accrete matter at even faster rates than previously thought. Furthermore, research led by Dominika Durovčíková and her team, using data from the Very Large Telescope, has focused on searching for Lyman alpha nebulae around young quasars. These nebulae, giant clouds of glowing hydrogen gas, could provide insights into the early stages of quasar evolution and the processes that fueled their rapid growth. While the mystery of quasar growth is far from solved, these ongoing research efforts continue to shed light on the extreme physics at play in the early universe. As we delve deeper into the hearts of quasars, we gain a better understanding of the evolution of supermassive black holes, the formation of galaxies, and ultimately our place in the vast cosmic tapestry.